Welcome to Choosing the Right Camera and Lens for Your Security Application, a training seminar brought to you by Tamron, New Eyes for Industry. There are several important considerations to keep in mind when selecting a camera for your security application. The first section of this seminar examines each of these considerations in detail. There are two main types of cameras, box cameras and dome cameras. Box cameras are not restricted in the size of the lens and can be equipped with long-range lenses to cover long distances. This is an important consideration in outdoor applications. Box cameras are generally large and conspicuous, providing added crime deterrent value to your security system. Dome cameras are generally more compact than box cameras, but this also limits the size of the lens. It is important to remember that some long-range lenses may be too large to fit inside a dome camera. Dome cameras can be effective crime deterrents because the direction of the lens is often not visible, making it difficult to guess the area of coverage. Once you have decided on the type of camera to use in your security application, you can consider the type of camera housing you will need. If your camera will be exposed to harsh environments or extreme temperatures, you may need a temperature-controlled housing to protect the camera. A wiper or defroster may also be necessary in cold environments. If the camera will be in an exposed area where it could become a target for vandalism, you may want to consider installing a vandal-proof housing on your camera. A day and night camera can take images in complete darkness using infrared. If you decide that you will need a day and night camera, consider the amount of ambient infrared illumination that is available. If little or no infrared illumination is available for your application, you will need a source of infrared illumination in addition to your camera. Be sure that you have considered the range of your target when determining the type and amount of infrared illumination you will need. Next, you will have to decide how your camera should transmit image data. Most security cameras in the world today are analog cameras. Analog cameras convert the images into a video signal that can be received by a television, monitor, or VCR. Analog cameras are popular because they are inexpensive and also because they use standardized video signal formats that are compatible with almost all analog recording systems and monitors. A drawback of analog signals is that they are susceptible to interference and noise and also cannot be encrypted, making analog cameras a poor choice if privacy or access control is a concern. IP stands for Internet Protocol. IP cameras convert the images into a digital signal that can be sent over the internet or stored on a hard disk. Although generally more expensive than analog cameras, IP cameras enable remote security because a digital signal can be carried over long distances. The signal can also be encrypted to restrict access to the images. IP cameras compress images using a variety of compression standards, so it is important to make sure that the IP camera you choose is compatible with your recording system. Camera resolution is a measure of the amount of information contained in the image and is commonly measured in number of pixels. A pixel is a single dot of color information in the image, and the color information from all the pixels make up the full image. The term mega means million, and a 3 megapixel camera has 3 million pixels. In order to determine the number of pixels you will need for your application, you will need to know how big your area of interest is and how many pixels you will need to represent that area. To calculate the number of pixels you will need, divide the number of pixels you need in your area of interest by the fraction of the entire image that area represents. Frame rate is a measure of the smoothness of the video signal and is measured in frames per second, or FPS. A higher frame rate will result in smoother motion capture, but will also increase the amount of image data that needs to be transmitted. For applications where there is little movement, a slower frame rate may be sufficient. For applications where action capture is important, you will need at least 30 FPS. Once you've decided on a camera, you will need to decide on a lens to go with it. The next section of the seminar will take you step by step through the various considerations in choosing a lens and will help you find the lens that is right for your application. The mount refers to the mechanical attachment between the camera and the lens. There are two common types of mounts for box cameras, C-mount and CS mount. The difference between the two lies in the distance from the contact point of the camera and the lens to the camera imager. This distance is 17.5 millimeters for C-mount and 12.5 millimeters for CS mount. Generally, a C-mount lens is used on a C-mount camera, and a CS mount lens is used on a CS mount camera. A C-mount lens can be used on a CS mount camera using an adapter ring. The adapter ring serves to increase the distance between the lens and the camera so that the image produced by the lens is aligned with the imager. It is not possible to use a CS mount lens with a C-mount camera. If you are using a C-mount camera, you must keep in mind that your choice of lenses is limited to C-mount lenses only. Dome cameras sometimes require a custom mount that is neither C nor CS mount. If you are using a dome camera that requires a lens with a custom mount, contact your lens manufacturer for detailed information on the type of lens you will need. Different cameras are equipped with different imager sizes, depending on the type of imager and the number of pixels. Standard imager sizes are referred to in units of inches, although this is not an accurate indication of the actual size of the imager. The dimensions of three common imager sizes are shown here. Lenses are designed to focus an image onto the imager so that the diameter of the image circle matches the diagonal of the imager. A 1/3 inch lens therefore has an image circle diameter of at least 6 millimeters to cover the 6 millimeter diagonal of the 1/3 inch imager. A larger lens can be used on a smaller imager. In this case, because the image captured by the lens will be larger than the imager, the angle of view of the image will become smaller, resulting in a telephoto effect. A smaller lens can also be used on a larger imager. In this case, because the image captured by the lens will be smaller than the imager, some pixels on the imager will not be illuminated by the image and will appear black. The focal length of a lens is usually measured in millimeters and determines the lens's angle of view. A short focal length provides a wide angle of view, and a long focal length provides a telephoto view. A lens can be either fixed focal, providing only one fixed angle of view, or varifocal, allowing adjustment of the angle of view over a specific range. For an angle of view of 90 degrees or more, select a focal length of less than 3 millimeters. If the target area is small or far away, select a longer focal length. In order to calculate the exact focal length you will need for your security application, you will need three pieces of information. The first is the distance between the lens and the target you wish to capture. You will also need to know the physical size of your target. And finally, you will need to know the size of the imager in your camera. Once you have these three pieces of information, you can use the Tamron online lens calculator to find an appropriate lens for your application. The Tamron online lens calculator is located at the address shown here. The F number of a lens is a measure of the light gathering power of the lens. A lens with a smaller F number has higher light gathering power and will deliver a brighter image. A lens with a large F number has lower light gathering power and will deliver a darker image. The F number of a lens is related to the required exposure time to obtain a clear image, and for this reason, the light gathering power of a lens is sometimes called the lens speed. A lens with a smaller F number requires less exposure time to obtain a clear image and can also be called a fast lens. The F number is calculated by dividing the focal length of a lens by the effective diameter. Some commonly seen F numbers in the security industry are shown here. To compare the light gathering powers of two lenses, compare the ratio of the squares of the F numbers. To compare a lens with an F number of 1.0 with a lens with an F number of 1.4, take the ratio 1.4 squared over 1.0 squared to obtain 2. This tells us that the lens with the F number of 1.0 has twice the light gathering power of the lens with the F number of 1.4 and will provide an image that is twice as bright. The iris or aperture is a mechanical device inside the lens that can be used to control the F number of the lens. The iris is approximately circular in shape and maintains its shape as it opens and closes. There are four main types of irises. Manual irises must be opened and closed manually by the user and cannot be controlled remotely. This type of iris is only suitable in unchanging lighting conditions or for cameras that have shutter speed control that can compensate for changes in the lighting conditions. The DC iris is the most popular type of iris. A DC iris is controlled by a galvanometer installed inside the lens. The camera converts light level information into a voltage that is used to control the iris. The video iris is similar to the DC iris, with the exception that the iris control circuitry is located inside the lens, and automatic light correction can be done in the lens circuitry. Due to the higher cost of this type of lens, video irises have recently seen decreased popularity. The newest type of iris is the P iris, in which a stepping motor is used to control the iris position. This allows precise control over the amount of light gathered by the lens. There are three main effects of decreasing the iris size. The first and most obvious is a decrease in image brightness. A smaller iris results in a darker image. A decreased iris size also results in increased depth of field. Depth of field refers to the object distance range in which target objects are in focus. A large iris results in a short depth of field in which only objects within a specific range appear to be in focus. A small iris results in a long depth of field in which objects appear to be in focus over a longer range of distances. Finally, a decreased iris size results in an increased effect of diffraction and can cause the quality of the image to deteriorate. Diffraction is the bending of a light wave when passing by a corner. Diffraction is an inevitable property of light and will occur any time light passes a corner. The effect of diffraction becomes severe when light passes through a narrow iris opening. To reduce the adverse effects of diffraction, Tamron has patented the Neutral Density Filter Iris, or ND filter iris. The ND filter iris uses filters to reduce the amount of light that passes through the iris when the iris is closed, allowing a larger iris size in bright lighting conditions. This larger iris size helps to reduce the effect of diffraction on the image, resulting in a clearer image. The resolution of a lens is its ability to resolve detail. An image produced by a lens with higher resolution will look more sharp than an image produced by a lens with lower resolution. Resolution is not constant throughout the image and is generally higher in the center and lower in the corners. There are three common units of resolution measurement: line pairs per millimeter, TV lines, and megapixels. Line pairs per millimeter is the most common unit of resolution measurement used to evaluate lenses. It is a measure of the number of distinguishable line pairs across 1 millimeter of length in the image. A line pair is defined by one black line and one white line. A lens with a resolution of 8 line pairs per millimeter can clearly resolve 8 line pairs, or 16 alternating black and white lines, across 1 millimeter of image length. TV lines is another unit of measure of resolution and is commonly used to evaluate cameras. TV lines is defined by the total number of black and white lines in the horizontal direction over the span of the height. Although megapixels is a unit commonly used to evaluate sensors and cameras, it can also be used to define the resolving power of a lens. Megapixels refers to the total number of pixels that can be captured, and since mega means million, 1 megapixel is equal to 1 million pixels. The total number of pixels in an image can be calculated by multiplying the number of pixels in the horizontal direction by the number of pixels in the vertical direction. For reference, a resolution of 1080p includes just over 2 megapixels. Resolutions can only be compared in common units, so it may be necessary to make unit conversions when comparing resolutions. Conversion between line pairs per millimeter, TV lines, and megapixels can be done based on the size of the imager. For reference, for a standard 1/3 inch imager, 1 megapixel is approximately equal to 865 TV lines and 120 line pairs per millimeter. When deciding on the resolving power of your camera and lens, remember that the resolution of the final recorded image can only be as good as the weakest element in your surveillance system. Information can only be lost as it flows through each element in the system. A low-resolution lens will capture a low-resolution image, even when used with a high-resolution camera. Different colors are represented by different wavelengths of electromagnetic radiation. The visible spectrum is represented in the narrow band of wavelengths between approximately 400 and 750 nanometers. The human eye perceives 400 nanometers as purple and 700 nanometers as red. Infrared rays, or IR rays, have wavelengths beyond 750 nanometers. Although IR rays are invisible to the human eye, most CCD and CMOS imagers are sensitive to IR rays up to about 1,000 nanometers. If you are using a day and night camera and require clear images in infrared illumination, you will need an IR-corrected lens to go with your camera. In a standard lens, the refraction angle of light depends slightly on wavelength, and different wavelengths focus on slightly different planes. Since infrared has a longer wavelength than visible light, it refracts at a wider angle than visible light and focuses behind the visible focal plane. This is called focus shift and causes blurring in the image. Tamron day and night lenses correct focus shift to focused infrared light on the same plane as visible light, resulting in a sharp image whether taken during the day in visible light or during nighttime in infrared. This is a comparison of images taken in visible and infrared light using a standard lens and a Tamron day and night lens. Both of the images taken in visible light are clear and in focus. When the lighting is switched to infrared, focus shift occurs in the standard lens, and the sharpness of the image deteriorates. Note the reduction in clarity in the image on the bottom left. Now compare this image to the one taken using the Tamron day and night lens on the bottom right. The Tamron day and night lens corrects for focus shift and maintains image clarity and sharpness even in infrared lighting. An IR-corrected lens must correct focus shift across a wide range of infrared wavelengths. Ambient infrared illumination can include wavelengths well above 750 nanometers, and most images are sensitive up to 1,000 nanometers. This means that an IR-corrected lens must be able to correct focus shift for infrared wavelengths between 750 nanometers and 1,000 nanometers in order to produce a clear picture in infrared. Tamron day and night lenses utilize special optical elements and advanced optical design technology to correct focus shift across a wider range of wavelengths than conventional day and night lenses. The difference may not be noticeable in visible and 850 nanometer light, but the images on the right taken in 950 nanometer light show a significant difference in sharpness. If you require a day and night lens for your security application, check to make sure your lens corrects for focus shift across the entire range of wavelengths your application will utilize. When choosing a lens for your security application, remember that the specifications given by the manufacturer are not necessarily an indication of image quality. Different lens manufacturers have different standards for rating lens resolution, and resolution ratings given by different manufacturers may not be directly comparable. Different lenses also work better with certain types of cameras than others, or may perform differently in different lighting conditions. Even the image brightness two lenses with the same F number can be different. That's why it's important to evaluate the lens yourself to confirm its suitability for your application. Examine the performance of the lens in extreme lighting conditions. Pay particular attention to the resolution in the corner of the image. If you are evaluating a day and night lens, test the performance over a wide range of infrared wavelengths. Only by evaluating the lens's performance in your specific application can you be sure that the lens is suited to your needs. For example, try evaluating your lens in strong sunlight and look for flare, ghosting, and other artifacts that affect the quality of your image. Be sure to evaluate an image taken in bright lighting using a small iris. This is a situation in which the effects of diffraction can have an adverse effect on the image quality. Check to make sure the resolution in the corners is satisfactory. For a day and night lens, check the image sharpness in longer IR wavelengths. Again, check to make sure the resolution in the corners is satisfactory. This concludes this training seminar. For detailed information regarding Tamron lenses and their applications, visit our website at www.tamron-usa.com. Thank you for watching Choosing the Right Camera and Lens for Your Security Application, a training seminar brought to you by Tamron, New Eyes for Industry.